Thanks for hanging around. I know we're running a bit over time, so I'll try to go through this as quickly as possible. Of course, I'll have the slides sent to you in email as well as the recording. So just real quick intro, I'm Harpreet Sahota, hacker in residence at Voxel 51. Been here for almost 2 years, and been working in deep learning for the last few years at various startups. And before that, previous life was an actuary, biostatistician, data scientist. So there's a lot of math and coding over the last, I guess, 15 or so years. You could connect with me on GitHub. Feel free to follow me to see what I'm up to. I'm shipping stuff quite regularly, so you might find something interesting in there. And if you'd like to connect, these are the ways that we can connect. So feel free to hit me up on LinkedIn, GitHub, or on X. So let's go ahead and just get into the content straight away. So we're going to talk about vision language action models, or VLAs. We've been touching on that a bit throughout the other talks. But I'm going to come at it from a perspective that I think matters most. And you might have heard this in the previous talk. It's about the data. But before we talk about the data, we got to go through what a VLA is. So I'll give you kind of a high-level overview of what we mean by vision language action model. So essentially, it's combining three fundamental capabilities into one unified framework. Of course, you've got vision, which is the ability to kind of perceive and understand the world through cameras and sensors. There's also language, of course, which is understanding natural language instructions from humans, and then action. So generating an executable command that will control the robot's movements. And unlike these traditional robotic systems that have kind of separate modules for each of these capabilities, VLA is going to integrate everything end to end. And typically speaking, the architecture has kind of five main components. There's three encoders, a fusion layer, and then the action decoder. So you have a vision encoder that's going to process that visual input, whether it's the camera images or sensors and whatnot, extract the visual features, and typically this might be done with some pre-trained vision transformer, or in the case of VLA, maybe like a model that is like CLIP or a CLIP-like model. And they're going to get converted into visual tokens. That's going to represent what it is that the robot actually sees. Then there's the language encoder that's going to process natural language instructions. This might be a text-only model like a BERT or a T5 to keep it lightweight, but increasingly we see more and more large language models that give us this rich world knowledge and kind of common sense reasoning. A common practice in recent times is to leverage a pre-trained vision language model, a VLM, that's kind of already been trained on this large scale web data to understand images and text. And the VLM backbone gives really broad visual and linguistic priors. And so we get a lot of decent common sense knowledge, some semantic grounding and reasoning capabilities. But a pre-trained VLM needs to be adapted to the robotics domain, right? The VLM understands semantics from the data, but it doesn't know how to ground that in physical action. And so you need robot-specific data to make this happen. You need robot demonstrations that are going to bridge this gap from the semantic understanding from the VLM backbone to executable motor commands. And so this is what distinguishes VLAs from pure vision language models. There's also this kind of what's called a proprioceptive encoder that's going to process the robot's internal states. And when we say proprioceptive, we mean just joint positions, velocities, torque, and effector of poses, gripper status, things like that. And these are just low dimensional vectors, maybe 10 to 50 values, and typically encoded using some kind of lightweight, encoder. Maybe might be an MLP or some type of layers like that. And this will be encoded into state tokens. And so we need this internal awareness because vision alone can't tell you where your own arm is relative to your body, right? And then we have this multimodal kind of fusion layer that's going to combine vision, language, the proprioceptive tokens, typically using some kind of transformer with cross-modal attention. And this will help the model learn to ground language concepts in visual observations while incorporating the robot's physical state. And then all of this gets sent to an action decoder. So it's going to translate this fused understanding into actual executable robot commands. This could be discrete action tokens, continuous values for, the joint angles, or, you see some models that use diffusion or flow matching to kind of generate a smooth trajectory that the robot should take. But here's the thing, you know, there's a promise with this, right? That general purpose robots can understand natural language and then adopt to new tasks without having extensive reprogramming. But whether that promise gets fully realized depends on the data that the models are trained on. So I want to focus on data and why it's so critical for vision language action models. And to do that, let's just first kind of appreciate how different robot data is from data that LLMs or VLMs have been trained on. So LLMs and VLMs, they've been hugely successful. And a huge part of that success is that they can leverage internet scale data. So billions of text documents, image caption pairs that are scraped from web, video transcripts, and all sorts of content that's out there, which is great. The data is abundant, it's diverse, it's easy to collect, relatively speaking, and it's out there on the internet. But unlike these VLMs that can leverage this existing web data, this web content, VLAs can't necessarily like just directly use this and train, robot policies because it lacks action grounding that's necessary for robotics. You might have data that's millions of people picking up objects, but those videos might not contain the right kind of joint angles, end effector poses, or motor commands that a robot needs to learn from. And so this kind of fundamental difference in the availability of this data is a bottleneck that current architectures just can't solve on their own. And so we need good quality data, cross-domain data. We need to use simulation to generate synthetic data. We need to use human videos by bridging kind of the human robot embodiment gap. And then, maybe some self-exploration methods where a robot could generate their own training data. And there are aspects of this type of data that are fundamentally different than kind of what a VLM or LLM is trained on. And so we're going to go into each one of these in more detail, but there's the temporal structure, right? So, but an action a robot takes, there's sequential dependencies. There's structure to an episode. We need to preserve causality. We need to model long-range dependencies, and the actions need to align with state transitions. Then there's the proprioceptive signal, which is the internal state that vision alone can't caption. It's low dimensional, but it's critical, and we need to fuse this with vision. And that's because precise manipulation in the real world requires this type of proprioception. There's also action grounding, so from semantic understanding to executable commands. So actions must work in the real world and just not kind of make sense only semantically. There's the embodiment, heterogeneity. Different robots have different data formats, so we can't really combine data sets from different robots. And the fundamental bottleneck is scarcity, right? This data, as was discussed previously, is expensive to collect, and it's limited in the scalability in terms of how we can collect that data. So we can't leverage like huge amounts of internet scale data like a LLM or a VLM can, because that type of data just doesn't exist for us. So let's go into each one of these in more detail, starting with the temporal structure, right? So if you have, let's say, image classification, let's just take a simple example. You have a data set that's just a collection of independent samples. So each image and label is going to stand alone. You can shuffle the data set, you could sample randomly, and model doesn't care about the order. But robot data sets are different. Each episode can be variable length, ordered sequence, and these are interactions between the robot and its environment. And then each kind of step in that episode depends on the previous states and actions. So to take an action, let's say at time t, depends on what happened at time t-1, t-2, and so on and so forth. And so the state that you observe becomes the consequences of the actions you took earlier. And so there's this temporal relationship that is critical for robots, or at least the models that we train, to understand, because they need to understand causality. So, for example, they need to learn that, if we move a robotic arm, if let's just say from the perspective of the robot, if I move my arm to the left, the visual observation is going to change in a predictable way. There's also the state transitions. So how does the environment evolve as a result of the actions that you take? And then also, again, the long range dependencies. So an action that a robot takes now might have consequences several steps in the future. There's a format called RLDS. We'll get into this later in the talk. And it emphasizes something called SAR alignment, state action reward alignment. And this preserves this kind of temporal structure in a way that makes it clear what the state was, what the action taken was, and then what the resulting reward or outcome was. So this temporal kind of structure is completely lost if we treat robot data just like, for example, image classification data, that is, as independent samples. But there's, a lot of data sets out there, don't have this kind of temporal structure built in. So action sequences in VLAs, they need to understand this long-term temporal dependency through this autoaggressive decoding. So this is one key kind of requirement of robot data. Next is the proprioceptive signals. So this is something that other types of data sets for image classification or video understanding don't have. And this is just the robot's sense of its own embodiment. So it has joint states, whether that's the position, velocity, torque for each joint in the embodiment. Also the end effector poses. For example, like however many degrees of freedom this embodiment has, the orientation of that. For example, here, if we have like a hand gripper, there might be 6 degrees of freedom, and then, the orientation of that gripper or that hand is important signal as well as the status of that gripper. Like, is it open or is it closed, and how much force is it applying? And this kind of internal state awareness is something that vision alone can't capture. So these kind of data, they are low dimensional, structured vector, maybe 10 to 50 values in total, depends on the robot. But it's just fundamentally different from just strictly visual input. But despite being low dimensional, it's essential for this really precise kind of manipulation in the real world. So vision can tell you where the objects are in the world, but it can't tell you where your own arm is relative to your body. So language can tell you what to do, but it can't tell you the exact joint angles that you need to kind of achieve a grasp. And so for this kind of accurate physical interaction and this really precise fine-grained control, you need both the vision and the proprioception. And so this is a unique kind of challenge that we face then in the multimodal fusion. So the signals need to be encoded. As I mentioned, it's typically using a lightweight kind of MLP, since they're lightweight, low dimensional kind of data, and they need to be fused with vision and language. The key point is just that unlike vision language models that are trained on web scale data and web data, we need to integrate this physical state information. And it's fundamental for making robots work. Of course, there's also the grounding in action, right? The action grounding. So this, I think, is fundamentally what separates just a vision language action model from just a vision language model. As we have drilled home so far, image and video give you some semantic understanding. They could tell you that picking up a cup involves grasping an object and lifting it, but they can't really describe what that action means in kind of like a more abstract term because they lack the motor grounding. They don't tell you how to actually execute those actions in the physical world. Robot kind of data sets have this, right? So they align their visual observations and language instruction with the executable action. So again, this is joint angles, end effector velocities, gripper commands, and just actual motor signals that move the robot's kind of embodiment. Of course, this action needs to be, depends on everything we talked about in the last couple of slides. It needs to be temporally coherent. You can't just predict independent actions at each time step. There needs to be kind of a smooth, physically feasible sequence of actions, right? If your arm is moving left at time t, then it can't be suddenly moving right at time t+1 without going through some kind of intermediate motion. Of course, this creates a gap. They call it the vision language action gap. So these multimodal models, they could achieve this kind of perception semantic alignment. They can understand what they see and what the language means, but they can't really turn that into a physical action, right? There's also this issue of embodiment heterogeneity. So this is a challenge that doesn't really exist in image classification or video understanding. Different robots are just fundamentally different. They have different action spaces. You might have a robot arm that might have 7 degrees of freedom, while a dual arm system has 14, or a quadruped robot might have like completely different control signals for its legs, for example. And so they require different proprioceptive observation spaces, different number of joints, sensor configurations, so on and so forth. And then also, of course, different sensor modalities. Some might have RGB cameras, some might have depth cameras, some might have multiple viewpoints, and some might just have tactile sensors. But the same action vector, it needs to induce this different motion for the different robots, right? So this is, for example, let's just say if I tell the robot to move its end effector to a particular position, XYZ position, right? That means something completely different depending on whether you're a single arm robot or a dual arm system or a mobile kind of manipulator. So this kind of kinematic structure of the robot is what determines how the coordinates are going to translate into actual joint movements. So of course, this is challenging as well, but we have something that we'll talk about later. Something called open X-Embodiment, and it kind of addresses this embodiment heterogeneity through this concept of like coarse alignment. So, unifying everything to a kind of 7 degree of freedom end effector representation, which is position, X, Y, Z, orientation role, pitch, yaw, gripper state. But even if we have this type of alignment, there's a lot of variation that we get amongst the different embodiments. And so this kind of heterogeneity is why this cross-embodiment learning is a challenge and why data organization and standardization matters. Of course, the scarcity of data, right? So unlike what we see with LLMs and VLMs that have internet scale data, the type of data I'm describing to you right now doesn't exist in a publicly available, at least, way that is really large in scale. A lot of it just comes through, having to do human teleoperation, for example. This is the primary method for collecting this kind of robot data. But that's labor intensive, it's costly, and it's limited in how you can scale that. And that's because you need to have expert operators who know how to control the robots. You need specialized hardware, the robots themselves, of course, which are expensive. You need real world environment setups with the object and tasks and scenarios. Of course, you need to do all this safely. And so this adds additional overhead and constraints. So while we have LLMs that are trained on trillions of tokens and VLMs on billions of images, these kind of robot data sets are just typically in thousands or maybe millions of trajectories. So of course, this restricts the generalizability and the robustness of these vision language action models compared to just their strict vision language model counterparts. But this kind of bottleneck that we face, it can't be solved by architecture alone. So you can design the best architecture for a vision language action model, but if you don't have diverse, high quality data, that model is not going to generalize. And so this is why we need new approaches to data collection, organization, and cross-domain utilization. Of course, you could have simulation, and this can generate synthetic data at scale. We have human videos that can be leveraged by kind of bridging the human-robot embodiment gap. We could have robots do the self-exploration, but all of these require careful data organization and curation in order to be effective. But before I go into, kind of how the field is organizing these data sets, I want to talk about benchmarks, specifically their limitations and what they reveal about the type of data that we need. So currently benchmarks measure model performance outcomes, right? They test the manipulation skills. Can the robot pick up the objects? Can they stack blocks? Can they open doors? Of course, they test language conditioning. Does the robot follow the instructions? They test robustness. Does the robot work in a different environment with different objects? They test cross-embodiment transfer. Can a model trained on one robot work on another? And while they give us these kind of measures, they don't tell us the type of data that we actually need. So what kind of data do we need to enable generalization? And then how does that, what's the importance of data quality compared to data quantity? And how does the way we organize these data sets affect the outcome? And I think these are critical questions for kind of understanding, at least from a data-centric perspective. And these are things that current benchmarks don't answer. And so really there's what I think are kind of a few key limitations of current benchmarks. There's this lack of unified standards. Different benchmarks will use different metrics, experimental setups. You might have a benchmark that measures success rate. You might have another that measures task completion time, and another might just use a different evaluation protocol. And so this makes fair comparison different across different models. So you can't really easily tell if model A is better than model B if they're evaluated on completely different benchmarks with different metrics. The second thing is that benchmarks are really limited in task complexity. So a lot of them focus on simple, short horizon tasks, pick up the object, move it here, stack those blocks, and they fail to really test, I think, this kind of advanced cognitive reasoning. So the multi-step planning, how to handle unexpected situations, how to adapt to kind of novel combinations of objects and tasks. And this limitation means that benchmarks really don't reveal whether the model needs more diverse training data to handle these complex scenarios. Third is just insufficient ways to probe generalization. Right? If we don't have a systematic way to kind of probe and assess the frontier generalization capabilities, and this is because they test on a fixed set of tasks, objects, environment, and they don't really systematically kind of test whether the model can truly handle a novel scenario. So this means that we don't know how well the models generalize beyond kind of their training distribution. And of course, the last one here is that a lot of benchmarks focus on binary success rates. So they might measure success or failure. Did the robot complete the task or not? But they missed this fine-grained metrics that would reveal how data quality and organization affect the model behavior. For example, like how smooth were the actions? How many attempts did it take? How did the model behave in edge cases? And these details matter for understanding what data strategies actually work. And so from these limitations, there's a few things that it reveals about the type of data that we need. So like I mentioned, when benchmarks don't probe on kind of systematic generalization very well, when they test on fixed sets of tasks environments, it suggests that the model needs more diverse training data to achieve more kind of robust generalization. So if the benchmarks can't even test generalization properly, then I think this is a sign that the training data might not be diverse enough to really enable the generalization in the first place. And I think the reason that these current benchmarks don't answer these questions is because they don't measure the data side of the equation. And this is a critical gap. We measure model performance, but we don't understand how the data strategies affect what the models can learn. So I think better benchmarks are needed for kind of measuring the impact of data. So, benchmarks that systematically probe generalization, that reveal how data quality and organization affects the outcomes. But the thing is that data organization and standardization, these are prerequisites for building a comprehensive evaluation framework. So we can't compare different strategies if everyone has data that's in a different format, that's collected under different conditions with different metrics. And so I hope this is why this is going to serve as talking about at least benchmarks and what they reveal as a bridge to the next section, which is about how the field is organizing data. So there's a few different data set formats out there that seem to be present in a lot of vision language papers that I've come across. There's RLDS, which is kind of the OG, if you will, and we'll get into each one of these in more detail. And this data set, it was, I believe, created by Google, and it is really good for preserving the temporal structure. So you get a lossless format for sequential decision making. And it solves the problem of this temporal dependency and episodic structure. And so we have episodes, steps, we have the state, action, reward, alignment, and then various tools to kind of transform the data set. And what we get from this is that we are then able to kind of get policies and train algorithms that can exploit this temporal information. Built on top of RLDS's open X-Embodiment. And so this is a massive effort that unified diverse data sets. So it's a data set of 1 million trajectories across 22 robots, and everything is in a standardized format. And so this solves the issue of this heterogeneity across robots and data sets. So there's this concept of coarse alignment and unified representation that this project focused on. And so this enables this cross-embodiment learning and just really shows how valuable diversity in the data set is. A newer dataset format that's been getting a lot of traction in the community is LeRobot. So the first ones are RLDS, OpenX embodiment. These are built on TF records, TensorFlow records. LeRobot is strictly PyTorch datasets. And so this becomes kind of practical. It's lightweight format with lossy compression, and it solves the issue of accessibility and sharing. And so if we're able to access more datasets and share more datasets, that means that we're able to kind of have more adoption for this dataset format and more kind of comparable ways to evaluate any VLAs that we train. So let's talk about each one of these in more detail. So first is RLDS. And so this addresses a really fundamental problem, which is how do you preserve what makes robot data unique when you store and share it? And so the answer that this paper presented was just to use a standard lossless format that preserves all the information from the environment interactions without making any assumptions about how the data is going to be used in the future. And so it maintains a temporal and episodic structure, and it has like a hierarchical organization. So we have a data set. Inside the data set, we have episodes. Inside the episodes are steps. And these steps will contain an observation, an action, a reward, and associated metadata. And so this preserves temporal relationships that's super critical for robot learning. And so this SAR, state, action, reward, what this means is that each step contains a state observation, the action that was applied to that observation, and then the reward that was obtained as a result. And this helps preserve causal relationships. And you could see, here's what the world looks like, here's the action that was taken, and here's what happened as a result. And what's super powerful about this is that it gives you a set of also just transformation tools that just enable any policies or models or algorithms that you train to consume data in different shapes. Right? You might have some policies that require full episodes, some that need maybe a shuffled transition, some that need kind of an n-step sequence. And it lets you transform this data into whatever format your algorithm or policy needs, and it just maintains that temporal structure. And this is useful because it enables reproducibilities. So you can share data sets exactly as they were collected. And so it enables more kind of easy data set generation as well. So you can record interactions and immediately have them in a standard format that you can then share with the community. And so this, of course, is what accelerates research. If we have data sets that are shareable without information loss, and we have some primitives for building a data processing pipeline, it just will, it's a flywheel for research. But the key structure, the key kind of point of this paper is that data format and structure matters. So RLDS preserves temporal structure, gives us a fixed set of transformation tools. This helps algorithms exploit this temporal information. And on top of this RLDS is OpenX embodiment. So the underlying format of OpenX embodiment is RLDS. So when you download OpenX embodiment, that's what you're getting. You're getting RLDS formatted data. But this is a massive effort that just attempted to unify robot data. So there's 1 million real robot trajectories that span 22 different embodiments. So everything from single arm, dual arm, bimanual robots, quadrupeds, just different embodiments and morphologies for robots. And so the data in this came from 60 different data sets that were collected by 34 research labs. And it scale of it is massive. So there's 500 plus skills that are demonstrated across 160,000 tasks. And the important thing is the organization, right? So all this heterogeneous data was converted into a consistent RLDS format. And because of that, they're able to then address this kind of embodiment heterogeneity, right? So they do this through this concept of coarse alignment. So everything that you get from all the different embodiments gets standardized into a seven-dimensional action vector: position, X, Y, Z, orientation role, pitch, yaw, and gripper state. And then the actions are normalized prior to alignment, then denormalized per embodiment when they're actually used. So this paper, this work that they did, demonstrated that really large-scale general-purpose models that are trained on a diverse data set can really outperform narrowly targeted counterparts that are trained on smaller, task-specific data. So what this paper showed was that models that were trained on this data set from multiple robot embodiments had massive improvement compared to models that were trained on just single embodiment data, even when they were evaluated on that same single embodiment. So this is powerful. Instead of going out there collecting new data and training a model kind of from scratch for each new robot, you could leverage a data set like OpenX embodiment. And so massive effort. But of course, it demonstrates that it's not just about the data itself. It's about kind of the organization of that data and standardization. And because of this organization and standardization, it enabled us to train models and policies that just were not possible to do before. Finally, we're going to talk about the LeRobot format. So this is kind of a new up-and-coming kind of data set format that is a project out of Hugging Face. So it gives you just a lightweight, kind of accessible alternative to lossless format. So it essentially uses lossy video compression and it reduces the data set size and kind of the bandwidth requirements to get that data, which in turn makes any data set that's out there or that you're collecting easier to share and distribute. And so this kind of design philosophy just makes practical deployment and widespread adoption feasible. And so the insight is, not everybody needs full lossless data. For a lot of training and evaluation purposes, some compression is acceptable. So the trade-off is you might lose some visual detail through compression, but you might gain accessibility. So LeRobot focuses on making data sets just smaller in size in terms of footprint on disk, faster to download, and easier to work with. Whole thing here is just sharing and distribution becomes a lot more easier. So the kind of important principle from LeRobot is just that different data organization strategies serve different needs. So we have RLDS for this lossless format and to preserve everything, which is perfect for research where you might need complete information. And then LeRobot is lightweight and it prioritizes accessibility. And both those approaches are valuable. The key is just having this standard in place because this standard enables this kind of interoperability. Right? So if everyone's using completely different formats and you can't combine data sets, you can't share tools, you can't build on each other's work. But if you have a few well-designed formats that serve these different purposes, you can enable the field to kind of move forward faster together. So why does all this matter? So let's go back to the 5 things that I talked about earlier about what makes robot data unique, right? So temporal structure was the first thing we talked about, right? RLDS format preserves this temporal structure. There's sequential dependencies between steps in an episode, and it has this state action reward alignment. This means that a algorithm can exploit causality, and a model can learn that moving the arm left causes some type of visual observation to change in a predictable way. It enables it enables the model to kind of understand a state transition, so how the world evolves as a result of actions. So without this kind of temporal structure, you lose a lot of information, right? Second is the proprioceptive signal. So we standardized formats using RLDS and open X-Embodiment. We ensure that there's kind of alignment across different modalities and embodiments. So the reading at time t aligns with the visualization at time t and the action taken at time t. And so we get a consistent representation across all the different robot embodiments out there, despite the different, number of joints they might have, or the configuration of their sensors, or whatever kind of kinematic structure they might have. And so this is what enables that cross-embodiment learning, and it preserves the internal state that vision alone can't capture. Action grounding, again, having your data set organized in this way preserves action sequences as a more just coherent trajectory, so they're not independent predictions. So this means that the model is now able to learn a smooth, natural movement and motion pattern. So organizing actions alongside observations and language in temporal sequences, this means that models that are, it enables those VLA models to work. We can ground, and we can have proper action grounding. So we can map from this semantic understanding to physical execution. The heterogeneity issue, open X-Embodiment, that coarse alignment that we talked about, this transforms this heterogeneity from barrier into a feature. So instead of seeing robots, as different as they are, as being incompatible, by having a standardized format, you could see them as just providing a different perspective on the same underlying task. So models that are trained on data from multiple robot embodiments, they tend to perform better than models trained on single embodiment data. Finally, the issue of scarcity. Right? If we're able to standardize data set formats, if we're able to organize this and combine data from different sources, then we can overcome this data scarcity challenge. Right? And of course, with this, with this massive amounts of data, we could do more curation so that we could kind of maximize the value of the data that we do have through filtering, augmentation, and optimization. So without organization, each of these challenges becomes insurmountable. But with organization, they become more manageable problems. So just to talk real quick about why data matters more than architecture. Well, first is the point about scale and diversity. Because without scale and without diversity, you can't have performance. So OpenX embodiment gives some compelling evidence in that paper. So models that are trained on diverse, large-scale data sets, they consistently outperform narrowly targeted counterparts that are on, models that are trained on just like narrow data sets, smaller task-specific, robot-specific data sets. Cross-embodiment actually improves performance, so that models that are trained on data for multiple robots just show better performance than models that are trained on single embodiments. This diversity improves learning. So different robots provide different perspectives on the same task, and having data sets organized in a way that we have described in a consistent standardized format, that means that we're able to train stronger, more robust models. Issue about quality over quantity. There's a paper from Hugging Face called Small VLA, which demonstrates this. So this paper showed that they achieved a really high performing model with a data set that was an order of magnitude smaller than state-of-the-art models. The way they're able to do this was just maximizing the quality and diversity of the real world data. So they had better data curation, better data filtering, and organization. And this mattered a lot more than just raw data set size. And it's a consistent pattern that we see over and over if you read enough survey papers on vision language action models. The pattern is there. Large scale general purpose models that are trained on diverse data
will always outperform task-specific models that are trained on smaller, more focused data, provided that we have curated, filtered, and organized the data in a good way. So let's go on and continue this, a couple more slides here. All this to say, everything we've touched on up to this point is just to say that architecture can't really compensate for a lack of good quality data. So pre-trained vision language models, they don't really transfer effectively to robotic tasks without robot-specific data. So you might have a model that's excellent at understanding images and languages together, but there's the action grounding gap. So the gap from the semantic understanding to physical execution can't be bridged by architecture alone. So you need robot demonstration data that shows how vision and language translates to action. But to get generalization, you need diverse data, right? So you need to have a model demonstrate performance in familiar scenarios. You need to have it be proficient, right? Really in familiar scenarios, tasks, objects, environments that are similar to the training data, but then, you can train that type of model and policy, but without diverse data that covers diverse scenarios, then it's not going to generalize outside of that, of course. Architecture innovations, they are helpful. They've been massive, but the gains that we get for VLA models are just incremental. You can have a better vision encoder, better fusion mechanism, better action decoder, but the improvement that we get is modest compared to the improvements that we get from better data organization and better data curation. So going from a single embodiment to cross embodiment training might give you some improvement. Going from small focused data sets to large diverse data sets might give you an even larger improvement. But the fundamental limitation is that architectures can't learn patterns that don't exist in the data. It can't create knowledge that isn't there. So if your training data doesn't include this diverse scenarios, your model is not going to generalize to diverse scenarios. So again, diverse, high quality data, prerequisite for generalization. Primary bottleneck is data scarcity. No amount of architectural innovation can overcome this fundamental kind of bottleneck. You could come up with a perfect, wonderful architecture, but if you only have 1,000 demonstrations from a single robot in a single environment, the model is going to be limited in what it could do. So architecture matters, but better data matters more. So just to wrap it all up, kind of the points I was driving home here. VLAs, they don't transfer without robot data. In order to get generalization out of VLA, you need diverse training data. But how do we get diverse training data? Well, we need consistent formats for our data set. And projects like RLDS, Open X-Embodiment, and LeRobot enable this. And taking together these kind of methods of organizing data sets and standardizing data sets, it helps us overcome this bottleneck of data scarcity. That is it for me. Thank you so much for hanging out.